briefly at the very start, Royce Zia, who's recently retired from Virginia Tech. So Royce, please go ahead.
Okay, thank you, Brad. Recent is like 12 years ago, by the way. So anyway, let me apologize to people like Brad and Leo, who probably heard bits and pieces of this talk as long as 15 years ago. Nevertheless, because this is a school and not just a colloquium, which is what the talk was based on, I will make lots of detours, and you will see the detours because I will clearly state that it's a detour and an end detour to give you a little bit more what I think might be possible points of confusion, okay? And finally, this talk will be about equilibrium versus non-equilibrium. So I'll try to keep a color code. Everything that is in equilibrium is in purple, and everything that is far from full dynamics is red because it's very difficult. And whenever I talk about non-equilibrium steady states, I'll try to use the color green. So, all right, with that apology, let me start by sharing my screen and start share. Let's see, how do I do this? Okay, now I should have turned my phone off, but I forgot. Hang on. Sorry about that. Okay, so as you can see, my title is rather long, and I have to say I've been rather jealous of speakers like Tom, whose title is just one word, or Suzanne and so on, with just 2 words. But nevertheless, here we go. Non-equilibrium statistical mechanics is a term you hear all the time, but the word non is a bit dangerous. And let me just say a couple of words about the word non, because as you know, nonlinear is not specific. You don't know what people are talking about: quadratic, polynomial, transcendental, algebraic, or whatever. And so to continue nonfiction, you don't know what is biography, law, art, music. And if you say somebody is non-white, you don't know whether they're talking about black, brown, yellow, red, green, blue, or violet. And the worst case scenario is to add the word non to sense, and then you just get nonsense. So be careful when you talk about non-something. Here we go, the outline. It's what is non-equilibrium statistical mechanics, and it's a personal perspective in the context of what I was talking about. The word non is very non-specific. There you go again. And so this is my version of personal perspective of non-equilibrium statistical mechanics. Why do we study this stuff? Well, that's easy. It's from curiosity-driven to dollar-driven research. What is being done at many places, and these are just where my present collaborators are. If I have time, I'll tell you about that, but otherwise I may just stick to some simple things. I want to thank my long-term collaborator, Beate Schmidtmann, and lots of people all around the globe, including these 2 people that you've seen recently. So the first section is what is non-equilibrium stat mag? Well, I want to put it into the context of my personal view of the spectrum of physics. So on the one hand, I put statics, which is boring and doable. On the other hand is dynamics, which is exciting and undoable. And then what do you do if you're a good physicist? You sneak off a little bit from what you can do and do perturbation theory. So this is steady states. This is periodic and quasi-periodic states and lots of other things, all the way to understandable chaos. And all of this is both interesting and doable. So let me give you some examples of things you know. In classical mechanics, x equal to constant in statics. It's not only boring, there's nothing to do. On the other hand, full dynamics is impossible, because if they don't believe you, just give them a non-conservative force and ask them where does the particle go, and generally that is not known. So you sneak off a little bit and you talk about x equal to vt, it's periodic and quasi-periodic things and so on. Let me go on to E&M. Electrostatics, everybody agrees that it's boring. The students may not agree that it's doable, but the professor insists that it is. And on the other hand is full E&M, and if you brought up on Jackson like me, you can look at chapter 17 and read about the things that are really not doable. So what do? You sneak off a little bit, you do magnetostatics, Maxwell's equations, AC power generation, and essentially most of the modern society is based on the technology that is sitting here, not full E&M. So in this context, I put equilibrium statistical mechanics on this side, and you expect me to put non-equilibrium statistical mechanics on that side, I bet. But no, it's actually fearsome fury. And I'll illustrate as to what I mean. Here's a picture of equilibrium. It looks very peaceful, it's sunset. But everything you can see that is interesting is not in equilibrium. The sun is obviously not in equilibrium, clouds are not, trees are not, the house is not. The only thing that may vaguely be equilibrium is a patch of dirty water over here. Well, that may look boring, but it's far from trivial. Now, one of the books that I always assign but never use for my StatMech class is Goodstein's States of Matter. And let me quote to you the beginning of this book, chapter 1.1, Introduction. The first sentence, Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. So it's not surprising the next paragraph begins with, perhaps it would be wise to approach the subject cautiously. Yeah, you see what I mean by it may look boring, but it's far from trivial. In particular, the Nobel Prize in 2016 is won by people who worked on equilibrium statistical mechanics. And here's Mike Kosterlitz, whose office I believe is just next to Brad's. And so, and I've heard the word Kosterlitz-Stylus transition being mentioned a couple of times already, and that's what the Nobel Prize was partly for. So let me give you some continue to give the watery illustrations. If that is equilibrium, then fearsome fury would be something like this. And here you see a couple of people trying to figure out how to survive this wave crashing on them. And if you zoom in on these guys, that's what you would find. And they seem to be quite happy and seem to survive okay. All right, so let me talk about non-equilibrium steady states then. Keeping along with the watery analogy, here I am in a canoe with my wife, and here is a non-equilibrium steady state, beautiful pattern that continues to be there as long as we keep paddling the canoe. So that's the sort of context I want to give. So let's be a little bit more serious and say what distinguishes equilibrium from non-equilibrium steady states, because they're both time-independent distributions. So let's start from what you learned from StatMech courses, assume you had taken one. So the fundamental hypothesis Boltzmann put in that nobody believed him at the time was that the probability to find a system in any configuration is all the same for an isolated system. So here's a pedantic picture. I put the system and isolated from the surroundings, and the probability, the star stands for steady state, time-independent state of a configuration is something like this. Now, here's where I would like to make a little detour in case there are students in the audience who's not familiar with the word configuration. And we use the word configuration to mean that if you specify the system you want to study, then C are all the variables you want to keep. Here's an example. If you want to talk about gambler playing dice, and the two dice is from an indistinguishable set, so 1 to 6, then you can count that there are only 21 configurations for each throw, and P then is a vector in 21-dimensional space. But if the dice is distinguishable, like all these different colors, then instead of 21, there are 36 of these configurations, and P is a vector in that dimension, 36-dimensional space. Now, you remember Yuhai's example of the active Ising model with 2 sites and 2 spins, and you see here that he has labeled 4 configurations. That's easy. And so P is a vector in 4-dimensional space, and that's something you can actually handle, and you may remember that's what he solved exactly. Ising model with n spins, you probably know, or at least some of you know, spins can take up or down, so it's 2 to the n possibilities, and that's the space. And some of you may play the game of Go, and you will recognize that it is 3 to the 361 because there are 19 by 19 places where you can have no piece, a white piece, or a black piece. That's 3 to the 361. How about the stock exchange? Well, I more or less picked this number because I discovered that the most expensive stock is about $500,000. And since money is discrete in sense, then that number is a little bit less than 10 to the 8. The next stock is down there, so it's 10 to the 6, and so on, so on, so on. So there are many, many stocks. And so P is a vector in this huge dimensional space. Now let's just talk about 2 particles on a ring. And to specify the system, you need the 2 angles, theta 1, theta 2, between 0 and 2 pi. And now suddenly you're dealing with infinity to 2 dimensions. Finally, we hit something that is in the first pages of your StatMech book, n classical point molecules in L-cube space. And there you need to specify both the momenta and the position. And so you have 6n dimensional space, and P is in a vector in this dimensional space. So there's a warning, distinguishable from indistinguishable particles. So if you do indistinguishable particles, you have to figure out how to count, and that's what the quantum StatMech chapters are all about. And you get Bose-Einstein and Fermi gas, Bose gas and Fermi gas, and so on. So turning to fields, say a temperature field of space, then you have an infinite number of possibilities at infinity to the 3rd points, and P is a vector in this dimensional space. So here we are doing hydrodynamics, and there are density fields, 5 at least, mass, velocity, energy. And so C is monstrous, and P is a vector in monstrous dimensional space. So this is the end of the detour about what a configuration is. Now, typically when we do physics things, there's an energy functional. You tell me what the configuration is, and I will tell you what the energy is. And P star then says that, okay, the energy of this system can never change, and eventually I would visit every possibility with the same probability, as long as the energy of the configuration is what I started with. That's what this means, right? And this thing then allows you to get a viable definition of what a temperature is. And so you know how to make a reservoir at that temperature, a big reservoir at that temperature. And when you bring the 2 things together, you would find and allow the energy to exchange, then the distribution here no longer is delta distributed in energy, but exponential, and you have the Boltzmann factor. Okay, so this leads to a highly successful description of systems in thermodynamics. And in fact, we sneak off a little bit from it and use it to talk about thermodynamics, not just thermal equilibrium, sorry. And the Industrial Revolution is based on those things. Of course, we all depend on experimentalists to tell us whether we got it right or got it wrong. Anyway, the whole point is that there's no time dependence. Everything is stationary. The only task is to compute averages of observables like this. For example, what is the average energy? You just stick the H of C in here and compute. But again, it may look boring, but it's far from trivial, okay? The point is that there's no trace of dynamics anywhere. And if you insist on imposing a dynamics somehow, of course, normally you expect for generally physical systems, you expect F equals ma to hold at the lowest level somehow. In any case, if you describe a general system like the stock market, you better make up a dynamics of some kind, and you can do it by using what is known as a master equation. And if you wanted to go into equilibrium, you better obey detail balance. And all of these concepts I want to make a detour about because this is also a school. But let me just say what the master equation is. It's just an incredibly simple equation because we're trying to find out how the probability to find a system in any configuration at any time changes with time. Think discrete, for example, just to be easy. So for U-high system, there are only 4 of these C's. Anyway, what you see on the right-hand side are R's, which are just the rates, and it's denoted by with how it changes from C prime to C or from C to C prime, and it is non-negative, and it is assumed typically in master equation to be constants in time. So you can pictorially draw it this way. If C is your configuration that you want to focus on, then C prime to C is this way, and C to C prime is that way. And if you want to tell your grandmother about what you're doing, you tell her about tubes with water in it, and the water, the height of the water is specified by this P, and the C is which tube are you talking about. And these R's are just pumps that pump the water from one tube to another. So C prime to C is from this to this, and C to C prime is the other way around. So this is an incredibly easy equation to understand and to work on. All right, so now that you understand what these terms stand for, then that is obviously a net current from C prime to C, the one way minus the other way. But this is not a fluid current, but a probability current. So you can think of this thing as the probability current from one to the other. So I'm going to make another detour for those of you who are familiar with the Langevin equation. Oh, forgot a E here. Langevin equation and the Fokker-Planck equation, and wonder what this is all about. So to do that, some of you are probably familiar with the concept of stochastic differential equations. Certainly you've heard about them quite a bit from various people in this school. So starting with F equals ma, what you want to do is to add a noise term, which is eta. And this is the Langevin equation. Okay, it's just an equation that generalizes F equals ma. So the noise term is a random force, and it's easiest to think about the discrete C's evolving in discrete time. So how does this how do the stocks vary from one day to the next? And it changes by this delta C, and it contains usually 2 pieces. One is, quote, a deterministic bit, and another one is a random bit. And this random bit is different at each time step, and is taken out of some distribution. Typically, is taken to be time independent, though, of course, that is not the case in real life. Think, for example, the stock market. And that the fact that this noise, the fluctuations, changes from one day to the next is what they are called volatility in stocks. Okay, so instead of a deterministic path, you would have something that is very noisy, jiggling around like that. I really love the Sid's phrase. He calls them tortuous paths, okay? Anyway, each time C is run, a different trajectory can be expected. And when you do many runs, you get an ensemble path like this. And you would immediately recognize that in the days of hurricanes, you talk about them as spaghetti plots, right? So this is basically talking about probability distributions of all possible outcomes, and it's a function of time. And it is essentially like, is exactly like chi-square in quantum mechanics. So starting from a stochastic differential equation, the Langevin one, you can derive a deterministic one for P of x and t, just like the Schrodinger equation for psi. For example, if you're just doing a random walk, going to the right and going to the left, you know very well that that eventually becomes a diffusion equation for the probability of where to find the walker. And of course, that is exactly the same form as the Schrodinger equation, except for this V term. All right, in general, let's forget about Schrödinger for now. In general, P is a conserved quantity, and therefore it obeys a continuity equation. And so it looks something like this. And then now this right-hand side is, of course, a probability current, strictly current density. Okay, so it must look something like that. And that is known as the Fokker-Planck equation. It's the thing for this fellow. Usually, Fokker-Planck equations have first and second derivatives. First derivative is called the drift term, and the second is called the diffusive term. Anyway, it is a limit of the much more general master equation in the sense that if you have the configurations, if the configurations have some metric associated with them, so in other words, like X, and the R's link only the nearby ones, and then what happens is that you would get differential equations instead. If you don't have that situation, if they can be linked all over the place, then you write a generally operator, something like that, where it's linked in many different ways, and you would recognize it is exactly the same form as the master equation, which is a linear equation, and we write L on the right-hand side. And this is just a linear ODE, and you say, hey, that should be very easy to solve. All I have to do is diagonalize the operator and I'm done. But then, so is the non-relativistic Schrödinger equation. And if that were easy to solve, you wouldn't have courses in quantum mechanics, right? Okay, so that's the end of the detour that is trying to give you a connection between the master equation, the Langevin equation, and the Fokker-Planck equations. So back to the master equation. Now you can see how easy it is in terms of what to understand. So the rates obey detail balance if they satisfy. This is what I learned when I was a student still on these things. And they keep saying, well, it obeys detail balance if the forward and backward rates is equal to the ratio of this, Boltzmann factor-like terms. And I just swallowed it. I had no idea what else to believe in or not. So let me make you another detour, and that is the fluctuation-dissipation relation. So remember that a stochastic differential equation contains both the deterministic and the random bits, okay? If you want the system to go into, or rather, let me put it the other way, if there is a link between the deterministic and the random bits, that's called the FDR, fluctuation-dissipation relation, then the system will settle into thermal equilibrium. This is also known as the Einstein relation because he published a paper on it in this famous miracle year. Other people have done it too, Smolachowski and so on, but it's known as the Einstein relation. So detail balance, which I mentioned a moment ago, is very much related to fluctuation dissipation and Einstein relation in the sense that they all are the conditions that drive you to equilibrium. So this is a thing that I learned before. However, the whole point is that detail balance is a much more general condition, has nothing to do with Hamiltonians or not. Kamagarh, I had always quoted it as called the Kamagarh Criterion because it was written in 1936. By the way, you can see that it's very important because if you're going to write an equation for stocks or predator-prey, then you have no idea what the Hamiltonian is, right? So you don't have equations that look like this at all. So that's the Kamagarh criterion, and Yuhai calls this term the cycle rule associated with how these are. I'm not going to go into the details of it. If you want to know more, ask me at the end and I'll tell you about the Kamagarh condition. And just like everything else, when I found out that it was done in 1936, I was quite impressed. And just last week, I found out that it was done in 1911. And here it is by Wegschneider in German. And so probably nobody read it. Anyway, there it is. So let's end the detour and come back to the master equation and the detail balance condition that is written this way. All right. So once you chose to have the rates that satisfy this condition, then you can ask, well, if I start the system in some initial configuration like this, how would it evolve? And that's this picture that I drew at the very beginning of this school. If you started somehow, you obeyed detail balance, how does it evolve toward this P star? And that is what I call fearsome fury. And that's what you guys have been doing for the last 4 weeks. That's what hydrodynamics is all about. That's what the word dynamics is. And hydro just makes it much, much harder than anything else, like the active Ising model, for example. Anyway, let's put all that aside and dynamics aside and focus on stationary states. So we can't solve this thing in general, but can we solve the situation when the left-hand side is equal to 0, when it doesn't change anymore? And the answer is, oh, well, if they obey detail balance, it's incredibly easy because the rates obey detail balance means that if I put e to the minus beta h in here, you can look up there and you can see, okay, this is 0. And then I just get 0, right? However, there's something more to this statement. It's not that simple. Remember, each one of these separate terms is a net probability current from C prime to C. When you satisfy detail balance, it means that all the net currents are identically 0. Okay? When you satisfy detail balance, it means there are no stationary currents. Does that remind you of something? How about electrostatics? So equilibrium statistical mechanics is like electrostatics. There are no currents anywhere. Okay? All right, so if you want to do this kind of non-equilibrium statistical mechanics for dynamics, it is generally very hard. Have you ever tried to find the full time dependence of the non-relativistic Schrödinger equation? The answer is no, that's usually very hard. So let me turn to a different class of non-equilibrium statistical mechanics. You see what I mean? There's a whole variety of nons, all right? And that is this thing that I drew a picture of at the very beginning. So, question, what happens if you insist on violating detail balance? If you're a good graduate student, you should always, every now and then say, hey, I don't want to do what you tell me to do. And just violate detail balance and see what happens. In particular, if you invent the model of some stochastic process, and you find that the most natural rules don't obey detail balance. So for example, Nigel's predator-prey, if you write down a stochastic version of that predator-prey model, Lotka-Volterra model, you would find that it does not obey detail balance. Then what happens? Well, you are guaranteed a stationary state because the whole condition looks like this, right? It's just a linear equation. It's very simple. Now, what you know is the left eigenvector trivially exists. What do I mean by that? Remember, this is think of that as a column vector, and this is a matrix. And the left eigenvector is a row vector that you can dot to the right-hand side. And what I have is that suppose every element on this row vector is 1, then when it's dotted into P, it is just the sum of P over all the configurations. And that had better be 1 by normalization, and DDT of 1 is 0. So what you can make sure and you can check is that the master equation as written has an eigenvector on the left-hand side that is trivial, and its eigenvalue is 0. Because that is the case, the right eigenvector is also 0. There must be a right eigenvector with the eigenvalue 0. And that is what you mean by P star, right? L of the right eigenvector is equal to 0, and that is your P star. We can talk about ergodicity. If you ask me, if you worry about that, you can ask me at the end. So what happens that in such a stationary state? So we know that this eigenvector must exist. You're guaranteed to exist. So if you use that, what happens to this eigenvector? What can we describe about it? The point is that the net currents are all time independent because the p stars are independent, but they don't have to vanish. Instead, they must form non-trivial current loops because whatever comes into a configuration must also go out, and they have to form current loops. Does that remind you of something? How about magnetostatics? So this kind of non-equilibrium steady state is similar to magnetostatics. And these currents are sufficiently important that I've labeled them K star, K for current. And it is simply, you find out what the steady state is, and you multiply by the rates that is already given to you. And what happens is that this will not be zero. Remember that in equilibrium, when they satisfy detail balance, this is automatically zero all the time. So the question is, do these things correspond to any physics? And if so, how do you produce them? The answer is yes, of course, otherwise I wouldn't be talking to you. And how do you produce them is by coupling them to more than one reservoir, whether it be an energy reservoir, particle reservoir, or any other kind of reservoir. So let me go back to this picture again. Here's Boltzmann's fundamental hypothesis. You isolate the system completely, or you put it together with a big reservoir and isolate both of them completely. And then all the currents are zero. But if you now put your system between two reservoirs, then you, in general, why would you want to do that? Well, here's an example. We are between a 6,000 degree thermostat and a 3 degree thermostat, if you like. And in general, then you have no idea what these things are. Now, I shouldn't say you have no idea. Terence Hill, that you and I talked about, actually show how to construct this P star from all the rates. However, that construction is so incredibly complicated that even when it has about 10 configurations, it becomes pretty awful. So it's much worse than equilibrium stat mech when you try to calculate the partition function. So I'm not going to go into that. Anyway, there's another one besides the Earth that is important to us, in particular you. And how about in and out in terms of particles? You better eat and you better do some workout, otherwise you'll be in trouble. When I first give these talks, I keep thinking about eating. So I thought, well, what happens if you imagine putting yourself into actually isolation or in a thermal bath of 98.4 degrees Fahrenheit, what would happen to you? And if you're not allowed to eat and not allowed to work out, it wouldn't be very comfortable, but you would last a few days, especially if you're allowed to drink water. But I had totally forgotten about breathing. So if you're not allowed to take in oxygen and dump out oxygen at all, then you would last just a few minutes, and that's it. So here is the final statement. There is no life in equilibrium. You just can't do it. All right, so that's a overview of what I think, or rather what my perspective of non-equilibrium stat mech is, especially in terms of these two pictures. One, these are just some of it, right? So detail balance is important. If you obey detail balance, or you're trying to get there and you want to know how you get there, or you don't obey detail balance, then we don't even know what happens when you get to steady state. Let me give you some motivation for it. Glass, for example, exists in an isolated system. These things sit in your kitchen cabinets and it evolves with detail balance. They are non-equilibrium because they don't have enough time to get into equilibrium. So it is like the ones that is on the left-hand side. By contrast, I keep saying the ecosystem cannot exist in isolation, and so it does not evolve with detail balance. It can never go into equilibrium, with quotes, of course, and never, and it settles into a non-equilibrium steady state. So let me come back to last October's Nobel Prize. As you well know, these are the two corners where they are awarded the Nobel Prize. One is about the climate system, and one is about glassy systems that are stuck in long living states that cannot get into equilibrium. So are there any questions or comments? I'll stop for a minute.
You have one question?
Yeah, Professor, I just have one clarification question. When
Sure.
you make the analogy of magnetostatics with the non-equilibrium process, do you mean the steady loop current can generate a steady magnetic field? Is that the
Okay.
case?
Okay, so unlike electrodynamics, there's no electric and magnetic fields in general, right? So think about, so the easiest thing to think about is imagine you have a biased random walk. So a walker that walks to the right more than to the left, but you put the walker on a ring, okay? And so whatever is driving the walker, so it just keeps going around the ring and over again. And if you look at that system, then you can show fairly easily that the P star, the probability distribution for where to find this walker is the same no matter where on the ring. It is the same, but there's a current. Compared to the biased, on the non-biased one, there's no current.
I
right?
see.
And there's no magnetic field anywhere. It's just this silly guy walking around. Okay.
I see.
So you can draw the same picture where the ring is a loop of some kind in, let's see, whichever is better for you. You put the predator on one side and the prey on the other side, okay? And first of all, the prey's population increase, then because of that, the predator's population increase, then it eats up the prey, so it has to come down, and then the predator goes down. So think of rabbits increase, then the foxes can increase, then all the rabbits get eaten and they go down, and they go around like this. Okay, that's the so-called predator-prey cycle. And now again, you don't have any notion of magnetic fields. At least we don't yet. So somebody might come along and says, hey, guess what? We can imagine something like a magnetic field and so on. But at the moment, we don't have that picture. Okay.
I see. Yeah, thank you very much.
And I want to reemphasize, these concepts can be applied to many different things, which are generally called stochastic processes, like the stock market, like predator-prey, like epidemics, COVID, and so on. And none of them have Hamiltonians, none of them have fields, and so on, or magnetic fields. Okay?
Royce, there's a second question.
Sure.
Hi, I was wondering if you could talk about like active systems, because a lot of times people
Right.
refer to those as being non-equilibrium and violating balance.
Right. So all active systems are non-equilibrium in the sense that each fellow, like for example, the swimmers and so on, they do bias walks. Okay, they have a direction, they choose the direction, and they do bias walks. And you put them on a ring, you see, many people that have given talks, including Suzanne and so on, talking about things that are really complicated. And so you put it in 2 dimensions and you see vortices and all those things come up. But if you make life easy and put them on a ring, all they do is just go around and around and around like this, okay? And so what happens in that case is that each individual takes an ADP, or bacteria, for example, and swims and generates a direction. So they have to violate detail balance. As soon as you turn the reservoirs off, you starve it off of ATP nutrients, or the other way, if you prevent it from secreting whatever they are putting into the waste, it would immediately die or die very fast. Okay, so the idea of detail balance is that you give as much as you take from the same reservoir.
There's another question.
Does that answer your question?
She said,
So could you elaborate on the generalized detailed balance?
That's a bit of a longer story. Let me see if I have time at the end. And I have some slides at the end, because if I get to it without, if I get to it, I will show the slides, okay? But it has to do with what Yuhai calls the cycle rule. And let me just say one thing which highlights the big difference between equilibrium and non-equilibrium state mag and detail balance, blah, 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 is the following. Think of doing just F equals ma of a single particle in a force field, okay? If the force field is the gradient of a potential, you know a heck of a lot about that system, agree? Detail
Yes.
balance is like that. Detail balance is essentially the condition that is curl-free. To violate detail balance is to say, guess what? I have a force field that is not conservative. Then what happens? Well, all hell breaks loose. And the nice thing about StatMech and the master equation is that the DDT operates on the probability density. And therefore, we know that there is at least one eigenvalue, the lowest one, in fact, that is have eigenvalue 0. And therefore, we know that it would go into equilibrium. Sorry, not equilibrium, stationary state. Whereas in the case of single particle dynamics, you have no idea what it would do. It could just take off. So non-conservative force field in general is much worse. Okay.
Bryce, I have a question.
Yeah.
The master equation you wrote is local in time. Do people ever consider possibility that the probability distribution in the past affects retardation?
They do. So this time is the same as that time, or if you like, this is what is known as this is for the students. This is for the students. This is what is known as a stochastic, Markov process, in which the change depends only on the time step before, just before, and not have memory. And there are many papers that is written on things that have memory. And in real life, of course, memory does come in and affects things fairly seriously, or can affect things seriously if the memory is, if the correlation in time is long. In particular, Brad, this is something you may appreciate, is that in the school, there's been a lot of talk about coarse graining, okay? And you cannot coarse grain a master equation and get another simple master equation. By coarse graining, you mean that you've eliminated some of these C's so as to have fewer C's by whatever trick you want to do. What I discover is that in certain cases of coarse graining, what that does is to generate memory.
Right.
Doesn't surprise you, right?
Thanks.
By coarse graining, you generate memory, right? Anything else?
Nope.
Okay, let me see if I can find where I was. I'm so glad that a Nobel Prize is given to non-equilibrium StatMech. Anyway, all right. Why study non-equilibrium state mag? Well, that's easy. Curiosity-driven to dollar-driven research. Okay, so the color code is blue is curiosity and red is dollar. So curiosity is from fun and games and fundamental issues. You better not say fun and games when you're applying for a grant. To practical applications or long-term implications, you know, those are fancy words you use. And that's the subtitle, pure and applied theoretical physics of this talk, okay? So fun and games, let me start with that. You can start with computer games. A lot of kids of your generation grew up with computer games and you know how to play them. And they can be simple, extremely simple. However, they can have surprising and unpredictable results. The one I like to quote always is Conway's Game of Life. How many people know Conway's Game of Life? If you stick up your hands, I can try to see. Good, there are some of you. Anyway, for those of you who don't know Game of Life, you can Google this, but don't do it 1 week before the final because you get hooked and then you flunk all your exams. Anyway, you can get it from Wiki and so on. But more to the point is that computer games are also the models that we work with. We put a lot of models on the computer, like the one that Yuhai talks about, the active Ising model, predator-prey is a model, and so on. But in addition to that, there's real-life games. Here's where I echo Sid's sentiments about experiments. You should go into the lab and see. And there can be also simple, like the things that Sid was showing, it's beautiful, and surprising and unpredictable. And I want to give you an example of Bohr's kitchen. And this is Thomas, who is a grandson of Niels Bohr, and he is at the Technical University of Denmark. And you remember this picture of something coming in, something going out. And if you're going to be in the kitchen, what the heck do you do? Well, you wash dishes. And in dishes, the water comes in, hits the plate, and goes into the sink, okay? And that's generally what you expect. If you don't put a plate in the way, it will hit the sink and make a ring. And this ring is known as a hydraulic jump. In a sense, it's in a lot of Sid's pictures when he talks about splashing and so on. You can see the hydraulic jump. But anyway, here is the paper. And it is published in Nature not so long ago. And literally, it's called Creating Corners in Kitchen Sinks. And there he is doing it a little bit more control with a nozzle on a circular plate that has a particular lip, and it's put in down into the middle. And when you do that, you expect by symmetry, the hydraulic jump would be a circle like this, okay? However, if you change the nozzle height and you change the lip height appropriately to certain values, the circle become a polygon like this. A pentagon, or an octagon, or a triangle, or even a geometrically impossible two-gon. So you can look it up as you like, and that was just a picture of what simple things you can do. That is a lot of fun. Now, as far as fundamental issues are concerned, so far, nobody can predict or hypothesize non-trivial P stars. So unlike Boltzmann, we don't have this luxury. We don't know what to do. So we don't know how to predict what a snowflake looks like, or what, well, the case of that ring, they actually know how to predict it. So that's good. So one of the things you learn about in StatMech is that the equilibrium state is unique, and it has a thermodynamic limit that doesn't depend on boundary conditions, blah, blah, blah. And none of that is known. And in particular, is shown that in certain cases, the stationary state depends on even the geometry of the system, whether it's a rectangular one aspect ratio or a different one. Another thing is, what about equivalent classes of rates? I've just finished telling you that if you obey detail balance, you will go to the same equilibrium state no matter what. You can choose one rate to be whatever you like, and as long as the other one is the exponential associated with it, you will get to that state. What is the same situation for non-equilibrium steady states? We have some answers to this, but it's not very easy to put into place. Here's a more interesting thing. When you have current loops, it reminds you of gauge theories. So I come back to the student's question about magnetic fields. So when you have currents, you think of the possibility of gauge theories. Is there an underlying gauge theory that would tell you about magnetic fields and so on? And of course, the role of detail balance violation. All of this is the final thing, which is how do complex patterns evolve that emerge from simple rules for just a few particles? And I'll tell you what some of the simple rules are. And if you like, this whole fundamental issue echoes what Nigel was quoting from Feynman's lecture on wet water. We are doing things in a primitive, halting, and confused way. And then he says the next great era of awakened Einstein, human understanding may produce a much better method of how to go about this. That is what is meant by fundamental issues. Even Feynman thinks that this is hard. So dollar-driven research. Well, every 100 years, or I should say first, the NSF listens to a committee, which is part of the National Academy of Sciences. And there are lots of committees. Ours is called the Condensed Matter and Material Physics Committee. And they meet and they come up with a big report. And the last one is 2010. And they list challenges of what there is for this century. So 3 of the 6 challenges has something to do with non-equilibrium state. One of them is exactly what I just said. How do complex phenomena emerge from simple ingredients? And another one is explicit. What happens far from equilibrium and why? And I've just finished telling you there's no life in equilibrium. So what is the physics of life? The other 3 have to do with nanotechnology, energy demands, and information technology. So interesting would be what happens in 2110. Some of you hopefully will be around to see. I won't. Anyway, the DOE, which is another big funding agent, has a similar committee that comes up with a similar thing. And they list 5 grand challenges. They're essentially identical to that of the CMMP, except they use more words, they're control freaks, and they drop life. So here we are. How do remarkable variations emerge from the complex blah, 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 and how do we control them? And how do we characterize and control matter very far away from equilibrium? And the next 3 have to do with nano energy and information technology. So that's how you get money. But the other way to get money is to say, hey, what I do have something to do with reality, and you talk about broader impact. And here I start to list things one after the other. You're not supposed to read every one of them, but it doesn't matter. What the point is that it goes across the scales. One of the themes of this school, from femto to the yato, literally from one end to the other. And Sid, I'm very glad, has mentioned several times heavy ion collisions and quark plasma, all the way to Ellen's talk about galaxies and so on and so forth. I will give you a couple of examples that I've worked on some time ago in this range, which is in the middle. But in the context of the summer school, Grisha and Jeff has told you about the basics, but here are all the other people that have contributed to various parts of this across the scale things. And of course, there are those who talk themselves all across the scales. Actually, I should put Sid over here as well. Anyway, that's my idea of what is curiosity-driven versus dollar-driven research. Are there any questions or comments?
Hi, Professor. I have a question. You mentioned application and implication in the dollar-driven context. So I'm wondering, what's the difference between application and implication? Because I feel like there could be some difference.
Well, normally applications. So this is not a physics question, but a semantic question, right? It's a question about English. Well, when do you use the word application and when do you use implication? So to me, applications have technology in mind, something that is associated with something that is immediate, okay? And implications is generally more long-term, you know,
I see.
whether it implies that you would understand something more in the future. Brad, maybe you're an English, native English speaker. Can you address that better?
No, I don't have any special insights into that.
I mean, application versus implication. Application is more immediate. You know, you can so let me give you an example for the student. Application of E equals mc squared is making nuclear power and atomic bombs. The implication could be either the survival or the destruction of our species. How is that?
Any other questions? Yeah.
I have a question going back to actually I guess the first part of the talk. Most of what you talked about with these currents between possible states of the system was that the currents are not dependent on time.
Right.
And I wondered if there are, so maybe one of the examples you gave involved a time-dependent current, but I wondered if there are other interesting things to be learned about cases, either where you're interested in the transient, and maybe that's what you meant in the glassy case, or where you have a system that's cyclic in some sense. So I'm thinking back to Nigel's case where it's not really continuous, but you know, maybe there's some time scale for the rabbits to repopulate or whatever.
Right.
Is there stuff to be learned there?
Yeah, absolutely. I mean, this is such an enormous field. I just can't talk about everything in general. So back to the master equation, what you have on the right-hand side is the divergence of a current. And so as long as P is changing, even if the rates are constant, the currents will be changing, right? So let me see if I can go all the way back there and see if I can find it. Even if the rates are independent in time. So here we are. So even if these things are time independent, as long as that is changing, these things will be changing, okay? And so that's a lot of what you were referring to about transients. And so that happens. Now, glass is a different story. What happens there is that the time evolution is so slow that these currents are tiny. They could be exponentially small. And it would take the age of the universe for these things to get you out of a local minima. Okay, so that's when these currents are teeny tiny and you're stuck there. And when you do it again, you're stuck in a different place and there's yet another teeny tiny thing and so on. Now, a lot of the school have been talking about climate, and you know and I know that there are tons of time dependence in here. The Earth turns. So the rates are going to depend on the spin of the Earth. The Earth goes around the sun. So this is going to have those periodic states, and so on and so on and so on. Okay? So when this thing depends on time, that's what I mean by fearsome fury. Does that answer your question?
Yeah, thank you.
So it's enormous. It's just enormous. All right. Any
Okay.
others?
I think you can go ahead.
Okay, where am I? Okay, so I'll try to tell you a little bit of what do we do? We, in this case, is now me and a number of my colleagues. So what we do is that we're not as bold as on the various speakers that you've heard is. So we study extremely simple models, so simple that we think that we have a chance of figuring out what's going on. And we don't pick these models out of the blue sky. We try to have some idea of where they come from. They're generally motivated by something that is real out there. And we use a range of methods. And here are a bunch of my collaborators, and you've seen two of them before. But in reality, what we do is we sit at tables with nice beer on Sunset and just chew the cud. I think this is the main difference between us and experimentalists. While they are stuck in dark labs because they want to see very minute things, we are doing something like this. But seriously, the simple models on one end, I label as blue, is one set is what we call driven diffusive systems. In fact, we wrote a review article called Statistical Mechanics of Driven Systems, but it's a very old book and it's it has some of the things that I say just now. But in any case, driven is the key word for out of equilibrium. Diffusive is the key word for conservations are crucial. And so it applies very much to what is going on in this school. Both of these things are crucial, right? But we do simple things in non-hydrodynamics. So we put particles on a checkerboard and move them around according to some rules and ask what happens. This is otherwise known as an Ising lattice gas. If you choose the rules so that it would go into equilibrium, you can study the steady state by Onsager. I told you quite a bit about it. You don't have to do just Ising. You can put more than one species like Go and so on and so forth on it. And then you can change the drive. You can either make it direct drive like a bias random walk or a random drive, do it one way and then back the other way, homogeneous and homogeneous and so on. And you can put quench disorder in it, put mobilities in it and so on. There are many possibilities. The other one is known as reaction diffusion. And this is more like the predator-prey, what Fisher calls ordinary and serious interactions of random walkers, serious being being eaten. Anyway, along those lines, you can talk about percolation. And directed percolation is something you heard quite a bit about from Nigel as a class. And then you can put on various spatial structures, simple manifolds to non-trivial terrains and so on. So let me come back to DDS and say that in general, it is about embedding n-dimensional objects in a d-dimensional space. And I put it as ND and the N like that. And I'll now tell you about some applications. One of them is protein synthesis. And this is putting point particles in a one-dimensional space, so a line. So all of you probably know that in order for your body to function, your cells continuously make what are called proteins. And what is a typical protein? It's like hemoglobin, the thing that carries oxygen around for you. And what happens is that a DNA unzips into a messenger RNA, and mRNA is now very famous because of the COVID. And a ribosome clamps on it at one end and walks to the other end, reading the code and producing the protein. And while one does that, another one comes on and goes on to the other end. So here's a micrograph of all these ribosomes and their attached and finished proteins. And you can put it onto a very simple model for something like this. Physicists are good at making spherical cows. So we put it on a one-dimensional lattice, and we put particles in on one side and take them out on the other side. And the rates that they move from one to the other is what the biologists call elongation. The rate at which they come in at the front, lines at the front, is called initiation, and the other end is called termination. This process is called totally asymmetric simple exclusion process. Totally asymmetric because it doesn't go back. Simple exclusion because this guy never sits on top of the other. Two ribosomes don't sit on top of each other. So just to tell you how old this model is, back in 1969, Julian Gibbs and his co-workers used this model in a couple of important papers to talk about protein synthesis. And 1 year later, completely independently, have nothing to do with it, a mathematician published a paper on this simple model called totally TASEP, T-A-S-E-P. And these two are later known to be tied together. And more recently, Tom Chow, Kiran Malik, and I wrote a review. I was asked to write a review on this role of non-equilibrium statistical mechanics associated with this TASEP model to biological transport. So that's embedding zero dimension things in one dimension. There are many, many other things that you can do as vector of passive or active particles. So you have zero dimensional things in 2 dimensions, and all the way to the other end, surface growth in molecular beam epitaxy. That's how your semiconductors are made, in which you have surfaces which move in 3 dimensions like this. So you have a surface that is wobbling, and so it's a 2-dimensional thing growing in 3 dimensions. And multi-species, certainly you're familiar with cars and trucks on the road. They're going in the same direction. And of course, biological motors, there are different kinds of biological motors. There are many, many different possibilities, and I would just list a whole bunch of them on the end without going through the details. Here's epidemics, which you have to deal with the last 2 years. And if I have time, I will go into these things. So here's a favorite question that Leo wants us to think about. What have we learned so far? And this is not about the conference, but about what we have learned so far in what we do by using these simple models. There are many surprises as well as they expected, and I'll just try to illustrate. The surprises, the most important one, the most surprising to us is what I call negative response. So in particular, if you go to the wall and turn up the thermostat, you expect the energy in the room to go up, yes? Well, sometimes if you do that, the energy in the room goes down. That's what I mean by negative response. And what happened is that these 2 fellows wrote me one day and said, our students had done simulations and they found negative specific heat. And for simulators, that's a real bad news. It suggests you have some error. And they said, should I worry? And I said, well, you're doing non-equilibrium, you shouldn't worry. And they said, well, it's all well and good. Can you convince us? So I thought about it, and eventually we wrote up an article for the teaching journal, and it's called Getting More from Pushing Less. Literally, having the energy go down when you turn up the thermostat, or I should have said differential conductivity, when you crank up the electric field, the current goes down. Okay, so you can have this. Another really shocking thing is that non-equilibrium so far, steady states, so far, we have not been able to formulate a zeroth law. Now, in case there are students who don't remember what a zeroth law in thermodynamics is, it says if you take one system like your coffee, put a spoon in it and let it come to equilibrium, they would be at the same temperature. If you take the spoon and make it, and if the coffee is in equilibrium with something else, let's say a chopstick, then the chopstick and the spoon are also in equilibrium. So A in equilibrium with B in equilibrium with C means that A is in equilibrium with C. That we have not been able to do in general. That's how bad it is. We don't even have a zeroth law. So there's no universal way of determining what the temperature is in a non-equilibrium steady state. So things that shock you that you've already seen are existence of brand new stationary states, what Feynman calls, we have no idea before we actually saw it that there are these roles, right? So they exist. So you remember Piles talk about the fact that there are no phase transitions in one-dimensional systems with long-range interactions. So what that really means is no long-range order, and this is what Yuhai keeps talking about, Merman-Wagner theorem, that has to do with continuous spins. Okay, there's no long-range order, but you better be careful because some people refer to phases as something, even though there are no long-range order. So TASEP, on the other hand, is a one-dimensional system, the one that I just showed you, which have different phases. There are changes in the phase transition, change from continuous to non-continuous, change in classes. generic long-range interactions, normally equilibrium, you associate short-range interaction and short-range dynamics to have short-range correlations. But when you go non-equilibrium, long-range correlation show up, and there are lots and lots of things that happen. So let me just briefly show you about tacit in the sense that here are the two control parameters at the two edges, all right? And this is set equal to 1, so I don't have to worry about it. And what we discover is that the phase diagram in the alpha beta plane has 3 different phases. One is called the maximum current phase, one is low and high density phase. And before I go into details, just for contrast, the Ising model, if you don't drive these particles, but instead apply a magnetic field on one end, 0, apply it on the other end, and let this thing go bigger and bigger, then the magnetization in the middle is always 0, and this is always one phase. In other words, the correlation link never diverges. By contrast, we have 3 different phases. And I'm not going to go into all the details because I'm kind of running out of time a little bit. I want to leave some time for questions. But all I want to say is that these 3 phases actually should not come as a surprise to you, because let me go back to the model here, okay? Forget about protein synthesis. You see this every day. You're driving along, there's a car in front of you, and there's a traffic light at the top, which is controlled by beta, and there's a traffic light at the beginning of the road that is controlled by alpha. So if both of these things are fast, if both the traffic light are not there, say, they just let you come in, okay, what do you expect? You come well, in. This thing would eventually, okay. Yeah, well, this thing would eventually, yeah. So this thing would essentially then just go into, this thing would essentially then just go into, oh, there's some echo. Okay, so this, so you know what happens, there's just some smooth traffic going along, or maybe dense or whatever. But what happens when this is very fast and that is very slow is you get a traffic jam, right? If this is very slow and that is very fast, you don't have a traffic jam. You have very few cars, all right? And that is exactly what these 3 phases are. So this is when the incoming and outgoing traffic lights are both fast, and it just chooses the current that's the maximum possible current. But if the incoming traffic lights is very slow and the outgoing traffic are fast and the outgoing ones are slow, you get a traffic jam, and otherwise you don't. So none of this is a surprise, but it's nice to see that in simple models, it actually comes about very easily. I will skip all the details. Oh, by the way, this is something interesting. If you set the rates to be just equal, right at the transition between the jam phase and the non-jam phase, this is something you also see. You travel along quite happily and suddenly you go crashing into the back of a jam and you sit in the jam. And this shock can go back and forth. So that's another interesting thing about non-equilibrium setback. So let me go briefly to the things that are expected. After all, non-equilibrium means time reversal is odd. And so we talk about currents and magnetostatics. So we have probability current loops, and if we have probability current loops, we can talk about probability angular momentum in much the same way that we talk about fluid current loops and fluid angular momentum. And there you don't use the word fluid to describe vorticity. So let me give you the most trivial example possible. If I have 2 variables, X and Y, that is wandering around stochastically like that, if I plotted in X, Y, they would just bounce around all over the place. Question, if I make a histogram of this plot, I would then, in this stationary state, right? I would get what I call P star, which is the stationary distribution of where these variables are. But you can also take a look at the currents by asking, how did they change from one point to another? And you suddenly discover that there's a curl going on. So to measure that, you measure the time lag covariance is a measure of this K. So we measure the variable at a time t and the variable, these are the different components at a slightly different time. So here you can measure it at one time and then you can measure it at a different time. And then what you can do is to take the cross product of these two vectors, and what you get is, of course, the area that is spanned between them. And when you take the derivative of that area, that is what you call normally the angular momentum. So it is just the anti-symmetric part of this product of time and the next time, okay? And you can study, since you have a time series, you can study the average, you can study the distribution. And now I would take an illustration from climate science. These are things I learned from Baylor and Jeff. And unlike the situation with predator-prey, these are what I call subtle currents. So the two variables that we chose to study is D20 and NiNo3, and they look like this. And for those who are not familiar with this language, excuse me for the climate scientists, NiNo3 is the average temperature in this region, the yellow region, okay? And so when El Nino comes, it comes crashing in and goes up, and otherwise it goes down. D20 is the position of the thermocline, and is the ocean is fairly hot in the top. You heard about that earlier, and cold at the bottom. And the sheet where it's 20 degrees Celsius is known to go up and down along with this El Nino. And so you take the data, which is over the many years that I've plotted here, and you plot it on the XY plot, and they look like something. They don't look like there's any sort of predator-prey-like situation. But if you take the angular momentum and you make a distribution, you see that it is heavily favored toward the negative side, and there's a subtle current loop associated with these two variables. And the double exponential tail that we're predicting, oh, I should have said, the blue is the data, and the gray is a simple model that is a theoretical model that is comes from a Gaussian approximation. So, you know, it's tolerable. In any case, the important thing is that the average angular momentum is actually smaller than the standard deviation. So unless you plot this distribution, you won't be able to see it. And it's very subtle manifestation of the fact that there is non-equilibrium steady state. It's not like Nigel's system where it is, you can see it wandering back and forth. So that was published not so long ago. If you want to read about it, here's Jeff and Baylor and postdoc and a graduate student. So this is at the beginning of the school, I mentioned that it was motivated by a workshop that we all attended at that time. And you see all these three gentlemen that were there, the non-equilibrium physics people talking to the climate people. And how do you participate? There are a whole bunch of range of methods. Instead of going through all the details, let me just show you odd ones, from simulations, very simple simulations, to solving differential equations, to fancy field theory, and to rigorous mathematical methods. And so the conclusion is non-equilibrium steady state come from an exciting frontier, full of surprises and open questions, from the fun to the fundamental. And remember, the word fundamental begins with the word fun. So you should always have some fun when you try to do physics. There are many potentially important applications, and there are a wide range of ways to participate. So come and join the party. All right, I hope you guys had a very good time. And at this point, I want to thank Leo, I assume he's in the audience, very much for putting on such a wonderful school for us. Thank you.
We have time for a few more questions.
Right, I saved time.
Thank you for this great talk. I have a question regarding to what you said about the cross graining of the states.
Yeah.
So you said that from cross graining these states, which follows a Markovian process, you can get like the cross grain states. They can form memory, and they generally have non-Markovian evolution.
Right.
So usually what we think about cross-graining is that the information of the original state is lost during the cross-graining. But recently I've seen some people, they can actually infer, recover some information of the original states from this memory of the cross-grain states. So does it mean that the information of the original state is actually somehow like kept in this memory of the cross-grain states? So it means information is not lost.
Right. So the really tricky answer, as far as I'm concerned, is how is that information encoded?
Mm-hmm.
Right. Because what I can say is the following. If you have the original system with fine grain, then if you believe that that system evolved in a Markovian way, then what you need is a certain number of initial conditions.
Yes.
Right? One for each configuration. What is the probability at each configuration? What happens when you coarse grain is that that information is lumped together into something else, right?
Yep.
So you lose information by coarse graining the initial configuration.
Yes.
So that is what is the key behind quote memory, is that by specifying not only the C at T, but C at T1, T2, T3, and so on, then you have enough information to keep going.
Yeah. Yeah.
So it's like looking at a differential equation with many, many derivatives, and then you can keep going. So, but as far as out here, at a later time, when you look at the evolution of the later time, how it encodes the information of how you have coarse grain, I haven't thought about it carefully. Maybe other people have done work on this level can answer your question better. How to extract this information? Now, that would certainly be an extremely important research topic. How do you extract information? By looking at, in particular, the evolution, right?
Yeah.
Because you need many, you can't just sample it in one point to get it.
Yeah.
You need many points.
Okay. Thank you.
Mm-hmm.
Any other questions? Yeah.
Do you want me to talk about the loops?
Well, first we have another question.
Okay,
Just a short question.
sure.
Could you say a few words about the connection between maybe turbulent cascades and the fluxes that one finds there, and non-equilibrium steady states with similar constant fluxes? Is there any hope that we might have a more complete description of turbulent cascades by leveraging the power of non-equilibrium statistical mechanics?
Well, how shall I say? I am very far from an expert on turbulence and cascades, so I'm not qualified to answer that question. But I am an optimist, so I will answer the question you originally asked by saying yes, there's hope. Okay, and this is always the hope, is that one of you young guys would come up with a overarching principle of how to deal with non-equilibrium stat mech, besides, just looking things one at a time. I mean, in non-equilibrium, we have the Boltzmann factor, and that covers everything. All that remains is to figure out what to do with the Boltzmann factor. Well, in non-equilibrium, we don't even have that. And so we keep getting surprised. Our interaction based on that keeps getting surprised. So I don't know how to answer your question. Maybe, are there any folks in the audience who want to answer that question? Brad, you?
Well, maybe we should leave that for our discussion session at 11. And maybe also the current loop question, because we're at the end of our time for this lecture. So
Okay.
let's thank Royce again.